Right, well, one or two people have asked me to go through the last few questions on the gravitational fields framework. So we'll have a look at that in this video here, starting with question 1 on page 9. And on question 1, page 9, we have this formula. And the question says, show that the gravitational field strength of the Earth at a height h above the surface is given by this formula. So how will we go about doing that? Well, we know that we have a formula for gravitational field strength, which is that. So we can say the gravitational field strength at the Earth's surface, GS, will equal big G times the mass of the Earth, ME if you like, mass of the Earth, divided by R squared, where in the formula they've told us that R is the radius of the Earth. So gravitational field strength at the surface of the Earth, Gm over R squared, R is going to be the distance from the centre, which is the radius of the Earth. We can then also write a similar formula for the gravitational field strength some height above the Earth's surface, which will be G me over, well, if R is the radius of the Earth and h is the height above the surface, we've got that formula. So gravitational field strength at the Earth's surface and for a height h above the Earth's surface. Well, all we've got to do then is to rearrange this. So we know here that, for example, G times the mass of the Earth will just equal GS R squared, just rearranging that formula. So we can replace GME with GS over R squared. And of course, that's just that. And we've got the formula that we were given at the start. Then calculate the gravitational field strength at a height 200 kilometers above the surface of the Earth. So that was part 1. Part 2. Well, what we could do, we could look up the mass of the Earth. We could look up the radius of the Earth. We could look up big G in our data book and then put h in as 200 times 10 to the 3 meters and work it out using that formula. Or, seeing as we've been given this formula, we may as well just use that one. So to calculate the gravitational field strength, we know at the Earth's surface it's 9.81. If we look up the radius of the Earth, and there we are, 9.22 newtons per kilogram for the gravitational field strength at height 200 kilometers above the Earth's surface. And then we've got a question that follows on here. An astronaut floats in a spacecraft which is in a circular orbit around the Earth. Discuss whether or not the astronaut is weightless in this situation. So a classic question here. A lot of students will assume that when we go above the atmosphere we become weightless because we can see astronauts in orbit around the Earth floating around, so we assume that there's no weight acting on them. Well, of course we know that that's not true, and in fact we've seen it here. Very often one part of a question leads on from another. We've seen here that actually in orbit 200 kilometers above the Earth's surface, the gravitational field strength of the Earth is not hugely less than it is at the Earth's surface. So why is it that we have this situation? Now in part B there are 3 marks. There's no way of knowing exactly what the mark scheme is going to allocate a particular marking point for. So here would be my answer, which would, I think, cover all the marks however they decided to allocate them. So the first thing really we need to understand is that the astronaut will still have a weight which will be given by their mass times the gravitational field strength at that point in the field. And the gravitational field strength, although less than at the surface of the Earth, it will not be 0. That's the crucial thing. So the first point here, I'm sure we're going to get a mark for, is realizing, because we've been asked to discuss, is the astronaut weightless? The answer is no, they still have a weight. Why is that? G is not 0. And so they're going to have a weight given by the mass of the astronaut multiplied by the gravitational field strength, which is not 0 here. Okay, well, what is happening then? Well, the astronaut, although they have a weight, they feel weightless because the weight is the only force acting and there is no supporting force. Now, I would put both of those points here. The idea that, because often sometimes the mark scheme will look for the fact that the weight is the only force acting. On other occasions, it might want you to say that there is no supporting force. So, those 2 points go together really. Astronaut feels weightless. The weight is the only force that acts upon them. There is no supporting force here, no normal contact force as we would have if we were stood on the surface of the Earth. And the third thing that I would say is that the weight is providing here the centripetal force needed for circular motion. Or instead of centripetal, you can say resultant force towards the centre, the circular path. That's what centripetal force means. Resultant force acting on the body towards the centre of its circular motion. And therefore the weight is providing that force. And there we are. Okay, in question 2 we've got a graph of gravitational field strength against distance from the centre of the moon, and we're asked to mark on the figure the area that corresponds to the energy needed to move 1 kilogram from the surface of the moon to a vertical height of 4,000 kilometers above the surface. So basically we know that for gravitational fields, gravitational field strength is the rate of change of gravitational potential with distance. So if we've got a graph of gravitational potential against distance, so for example for a planet, graph of gravitational potential against distance would look something like this, where that's the radius of the planet there. The gradient at any point of that graph of gravitational potential against distance will give us the gravitational field strength. On the other hand, of course, change of gravitational potential is G delta R. Gravitational field strength multiplied by change in distance. Now, of course, if gravitational field strength is changing, as it will be here, then that will be the area under the graph of G against distance. Because these quantities are multiplied together, it's the area under this graph. In other words, change in gravitational potential, which is the change in energy of a 1 kilogram mass, will be the area under this graph here between 1700 meters, which is the 1700 kilometers, I should say, which is the radius of the moon, and 4,000 kilometers above the surface. Well, that's 1700 plus 4,000 is 5,700. So the area between those two dotted lines will give us the change in energy of a 1 kilogram mass moving between those 2 points. And then in part 2, what have we got to do here? We've got to estimate the change in gravitational potential energy of the satellite when it is moved from the surface of the moon 4,000 kilometers. So okay, when it has this transition from here to here, what will be the change in energy for a satellite of a mass 450 kilograms? Well, we know change in energy, work done moving it, will just be mass multiplied by change in gravitational potential. Remember, delta V, change in gravitational potential, will be the change in energy of a 1 kilogram mass. Gravitational potential is the work done moving a 1 kilogram mass from infinity to that point in the field. So delta V, whenever you work out change in gravitational potential, that is the change in potential energy of a 1 kilogram mass moving between two particular points in the field. So if we can work out delta V, the change in energy for a 1 kilogram mass, if we multiply that then by the mass of the satellite that we have, we'll get the change in energy for the satellite. Can we get delta V? Well, we've already discussed it's the area under this graph then. Now, how are we going to get that? Well, basically we need to count the number of squares under the graph, know how many squares we've got, and then multiply by the area of one square to get the total area under this graph. And how are we going to do that? Well, the way I did it was I just quickly counted the full squares. So I basically split this into columns in here, just including the full squares, didn't bother with any half squares to begin with. And then just at the bottom of each column I totaled up the number of squares. So the first column I got 12, next column I got 10, next one I got 9, and so on. Did that for all of them. Got the number of whole squares, out of those it came to something like 87 or something like that. And then roughly added up the half squares, just very roughly. That came to about 10 or so. So I think I got 98 squares roughly. So area under the graph, put delta V, area under the graph. My estimate was 98 squares. You might get a little bit more, a little bit less. I think the mark scheme said 90 plus or minus 10. And then we need the area of one square. So if we look at our our graph, horizontally each square is 200 kilometers. 200 times 10 to the 3 meters then. 1,000 kilometers is 5 squares, looking at that scale. And then going upwards, each one square is 0.1 newtons per kilogram. And so, if we work that out, we're going to get 2 times 10 to the 4 joules per kilogram. That's for one square. We then need to multiply that by 98, because we have 98 squares, not 1. And we will get 1.96 times 10 joules per kilogram. So that is the total area under the graph. Between 1,700 kilometers and 5,700 kilometers, simply by working out the area from the number of squares multiplied by the area of one square, which we have there. That will give us the total area under the graph, and we have that answer. Now, of course, then we've got to work out the work done. So that is the energy gained by 1 kilogram mass. That's the energy gained per kilogram. We haven't got 1 kilogram. We've got the mass of our satellite that we're moving from the surface of the moon is 450 kilograms. And there we've got an answer. Be careful about quoting too many decimal places. I mean, that really is an estimate. We've been quite rough in our estimate of the area under the graph. It's not easy to count up those squares quickly, particularly if you're doing it under time pressure. The key thing I would say there is try and be clear about what you've done, because it would be very easy to miscount these squares when you're doing under time pressure. Make clear what you've done, because you're only going to lose 1 mark if you count the number of squares slightly wrong. So I've tried to show there here, delta V is the area under the graph. What is the area under the graph? It's 98 squares multiplied by the area of 1 square. Well, the area of 1 square is, if you work it out, each horizontally 1 square is 200 kilometers, 200 times 10 to the 3 meters. Vertically, you've got 0.1 newtons per kilogram of gravitational field strength. There's the area of 1 square. Hence, we can get the area of 98 squares. Realise that the area under a graph of G against distance, gravitational field strength against distance, will be delta V. Okay, that is the change in gravitational potential. In other words, the change in gravitational potential energy for a 1 kilogram mass moving between two distances. And of course, once we've got it for a 1 kilogram mass, it is then trivial to work out what the energy change would be for a 450 kilogram mass. NASA now decides to bring the satellite back to Earth. Explain why the amount of fuel required to return the satellite to Earth will be much less than the amount required to send it to the moon originally. Well, I mean, the answer to that simply is going to be that the gravitational field strength of the Earth is much stronger than the gravitational field strength of the moon, and therefore the work done against gravity moving it away from the moon, and moving it away from the Earth rather, will be much greater than the work done moving it away from the moon. Question is, how are we going to explain that for 5 marks? So 5 marks, what sort of points are we going to need to make? Really, we want to just try and make as many points as we can about this situation that use relevant physics. If we can refer to any equations, that's always a good idea. So let's have a look here. First thing, do we understand that work must be done to raise the satellite to a point where the resultant gravitational field strength is 0? So if you can imagine the moon down here, you've got the Earth over here, there will be a point closer to the moon than the Earth where the resultant gravitational field strength is 0. Now, if you can get to that point, the Earth's gravitational field will naturally pull the satellite back from that point onwards. So it's really getting over that point there, and then you're home free after that point, that the Earth's gravitational field will continue to accelerate the satellite back to Earth. So it's reaching that point there. Now that point is going to be closer to the moon than the Earth, because the gravitational field strength at the Earth's surface is only 1.7 Newton per kilogram. How do you know that? Well, look at your graph. You know that the radius of the moon is 1700 kilometers. If you read off that graph at 1700 kilometers, the gravitational field strength is 1.7 Newton per kilogram. If you do 9.81 divided by 1.7, it's 5.8. So the gravitational field strength of the moon is 5.8 times smaller than that of the Earth. And that is due to the fact the mass of the moon, of course, is much less than the mass of the Earth. So I mean, all those points could potentially score points. One thing perhaps we might also realise is that the rocket weight will be less on leaving the moon than it was on leaving the Earth, because of course it used up some of its fuel on the outward journey, so it's lighter now when leaving the moon. So when it leaves the moon, it's leaving a body with a smaller gravitational field, and it has less mass itself as well. So both of those things are going to reduce the amount of the gravitational potential energy that satellite needs to be given to leave the surface of the moon, and compared to what it needed to be given to leave the surface of the Earth, because both the mass of the rocket M is lower, and delta V, the change or the increase in gravitational potential that it needs to reach this point here where the G fields cancel out, will be lower because of the smaller mass of the moon. So we're going to need less energy. Of course, if it doesn't need to gain as much gravitational potential energy, it doesn't need to be given as much kinetic energy to begin with, and therefore you're not going to need as much fuel. So those are the kind of points we need to be making. Difficulty with that question is thinking, well, I have 5 marks, you know. I kind of realise, yes, that it is going to be less, but how do I explain that? Well, just think about what's happening here. You're trying to get over this point where the fields cancel. The G field, going to make sure, notice it's weaker. If we know how many times weaker, that will be a good thing to put in. That might score a mark. Relate the relative masses of these two bodies. And this idea here, I would link to M delta V. You know, that we're trying to give a rocket of mass M a certain amount of a certain change in potential, so we can work out the gravitational potential energy needs to be given. Both of those M and delta V are both going to be lower for this homeward journey. Explain what is meant by gravitational potential at a point in a gravitational field. Well, really we just have to learn that. It is the work done moving a 1 kilogram mass from infinity to that point in the field. Just remember, gravitational potential, it's measured in joules per kilogram, so we're always talking about a 1 kilogram mass, 1 kilogram test mass if you want, and the zero of potential energy is always at infinity. So it's the change in energy moving a 1 kilogram mass from infinity to the particular point in the field where we're measuring the gravitational potential. Use the following data to calculate the gravitational potential at the surface of the moon. The mass of the Earth is 81 times greater than the mass of the moon, and the radius of the Earth is 3.7 times greater than the radius of the moon. Okay, so what do we know? We know that V equals Gm over R. Questions in our data book. Okay, well, big G is 6.67 times 10 to the minus 11. We know that the mass of the moon will be 81 times smaller than the mass of the Earth, and we know what the mass of the Earth is, 5.97 times 10 to the 24. So we've got to divide that by 81. And that's all divided by then, well, if we want to find gravitational potential on the surface of the moon, we need to use the radius of the moon as R. Now we know the radius of the Earth is 3.7 times greater than the moon, so the moon is 3.7 times smaller than Earth. It's 6.37 times 10 to the 3 kilometers, so times 10 to the 6 meters for the Earth. And we know that it's 3.7 times smaller on the moon. So we just need to calculate. And we get minus 2.86 times 10 to the 6. And don't forget the unit gravitational potential. It's always measured in joules per kilogram. Part C, sketch a graph below to indicate how the gravitational potential energy due to the Moon varies with distance along a line outwards from the surface of the Earth to the surface of the Moon. Okay, well, we know we've got a formula for gravitational potential here. So basically here we know that as r increases, as we move away from the surface of the Earth, the value of v will drop. Well, it'll be the magnitude anyway will drop. Obviously it'll become less negative, so the gravitational potential is actually increasing as you move away from the surface, and therefore it will curve away like this. But you will reach a point as you come towards the Moon where the gravitational, the mass of the Moon will start to kick in, and so as you move closer to the Moon, again it will start to lose gravitational potential energy again. So you, to begin with, you're increasing the gravitational potential energy of a 1 kilogram mass as you move away from the surface of the Earth, but then as you get close to the surface of the Moon, it will be decreasing again as the Moon's gravitational field starts to take over. And so what will happen is it will begin to curve down again a little bit there, where that is the surface of the Moon. So of course we'd have to give a 1 kilogram mass gravitational potential energy to move it away from the surface of the Moon and to move it away from the surface of the Earth. So there's going to be a peak here to this curve between the Moon and the Earth, but it's going to be closer to the Moon. I mean, generally we're going to have to put much more energy in to move a 1 kilogram mass away from the surface of the Earth than we are from the surface of the Moon, because the gravitational field of this is much, much weaker. The challenge question on page 12, the first part really is referring to Newton's law of gravitation and the fact that when Newton first came up with this law, and basically we were able to measure the force between two masses and determine a value for g, Newton's gravitational constant here. Basically that was akin to weighing the Earth, because of course once you know what g is, you can measure the weight of an object and then hence determine what the mass of the Earth will be. So, you know, imagine taking two very large lead spheres. Well, they've done this presumably early on in physics, measuring the force between them, and then working out big G. Once you know big G, we can work out the mass of the Earth. How could we do that? Well, if I know the radius of the Earth, which we can determine, if we measure the circumference of the Earth, we can determine its radius. And we're told in the question here that's 6.4 times 10 to the 6. And the gravitational field strength at the surface of the Earth is 9.8 meters per second squared. So basically, if we have a 1 kilogram mass in the Earth's gravitational field, we know it will experience a 9.81 Newton per kilogram, or Newton force. We know that big G is 6.67 times 10 to the minus 11. We're going to try and work out the mass of the Earth. We know that on a 1 kilogram mass at the Earth's surface, we get a 9.81 Newton force. And we've determined, or it has been measured, that the radius of the Earth is 6.4 times 10 to the 6 meters. Got to square that, don't forget. And all you need to do is rearrange that to work out m. And if you do that, you will get the mass of the Earth. Somewhere around 6 times 10 to the 24 kilograms. There you go, that's all there is to it. We cannot measure the acceleration due to gravity on the surface of the Sun in the same way as we can on the surface of the Earth. To find the mass of the Sun, we need to know the period of a planet in orbit around the Sun and its distance from the Sun. The Earth is 146 million kilometers from the Sun, and it orbits the Sun in 1 year. Calculate the mass of the Sun. Well, okay. So, if we're looking at orbital motion, what we know is the gravitational force is providing the centripetal force for that motion. Gravitation, so big M here would be the mass of the Sun, Let's put that in mass of the Sun, mass of the Earth. And the Earth, of course, is carrying out circular motion here around the Sun. So the gravitational pull of the Sun on the Earth is providing the resultant force needed for the Earth's circular motion, mr omega squared. Now, of course, we can cancel the mass of the Earth here. And so what have we got? We've got big G times the mass of the Sun divided by r cubed, where r here is the Sun-Earth distance. It's going to equal omega squared, where omega, of course, is 2 pi over the period. So if we rearrange this, t squared will equal 4 pi squared r cubed over big G times the mass of the Sun. Of course, I really want the mass of the Sun. Should rearrange that differently. So that's going to be 4 pi squared r cubed over G t squared then. So let's work that out. 4 pi squared. Distance between the Sun and the Earth, we are told that's 146 million kilometers. 146 million. And then kilometers, so we've got to times 10 to the 3 as well. And that's all got to be cubed. Big G, 6.67 times 10 to the minus 11. And the period, well, it's 1 year. And 1 year is 365 days, 24 hours in a day, 60 minutes in an hour, 60 seconds in a minute. And all that's got to be squared, of course, because it's t squared on the bottom. It's a question then of putting that into your calculator, and that comes, as you would expect, to a big number. 1.85 times 10 to the 30 kilograms. So always when you calculate a number like that, think, is it sensible? We know the mass of the Earth is 5.97 times 10 to the 24, so we're expecting something significantly bigger than that. Well, it is significantly bigger. Okay, well, 3A part 1, use data from the article to calculate the closest distance from the star to the black hole. So in that paragraph, or several paragraphs of information you've got there, it says that this star that's orbiting close to the black hole, supermassive black hole at the centre of the galaxy, comes at one point within 17 light hours of the black hole. So 17 light hours. What's a light hour? Well, a light year is the distance travelled by light in 1 year. So a light hour is the distance travelled by light in 1 hour. So how far is that going to be? Well, we know speed is distance over time. So distance is just speed multiplied by time. So the speed of light is 3 times 10 to the 8 meters per second. And an hour is 60 minutes or 60 seconds. So 60 minutes, 60 seconds in a minute. So basically we've got 3,600 times 3 times 10 to the 8. And that will give us 1.08 times 10 to the 12 meters. So that is 1 light hour. So you might think a light hour is a unit of time. It's not, it's a unit of distance, just like a light year is a unit of distance. It's the distance travelled by light in a particular period of time here, in this case 1 hour. So if we've got 17 light hours, well, we've got 17 times that distance. So 17 multiplied by 1.08 times 10 to the 12 will equal 1.84 times 10 to the 13 meters. It really doesn't mean much in meters, which is why they tend to refer to it as something like light hours, because the distance travelled by light in an hour has got some sort of something we can perhaps imagine a little bit better than, what does 1.84 times 10 to the 13 meters mean. Part 2 then. Calculate the centripetal acceleration of a star moving at 5,000 kilometers per second at the closest distance. Well, we know centripetal acceleration is v squared over r, so we've just got to be careful about units here. 5,000 kilometers per second Well, a kilometre is 10 to the 3 metres, so 5,000 times 10 to the 3 metres per second. And v is squared when we're working out centripetal acceleration. We need to divide that by the radius of the orbit. So the distance from the centre of the black hole, the distance of the star from the centre of the black hole, we've worked out here to be 1.84 times 10 to the 13 metres. So if we work that out, we can work out the centripetal acceleration of the star as it orbits the black hole at that distance when it's moving with that speed. And we come out with 1.4 metres per second squared. Assuming that the star is in a circular orbit around the black hole, estimate the mass of the black hole. Right, okay. How could we do that? Well, we know that gravitational force then is providing centripetal force. So we know that G, mass of black hole, put MB, mass of black hole, multiplied by the mass of the star, over r squared has got to equal mv squared over r. We can cancel the mass of the star. We know v squared over r is 1.4. So what have we got here then? We've got 6.67 times 10 to the minus 11 multiplied by the mass of the black hole over the distance from the centre of the black hole to the star, which we know is 1.84 times 10 to the 13 squared. And that's got to equal the centripetal force, which we know is 1.4 metre per second squared. So we just need to rearrange this. So if we take 1.4, we multiply that by 1.84 times 10 to the 13 all squared and divide by 6.67 times 10 to the minus 11. We'll get our answer for the mass of the black hole. So that comes to be, well, there you go, I'll come out with 7.1 times 10 to the 36 kilograms. Maybe should have kept an extra significant figure there, and rather than rounding to two significant figures, because I'm going to get a little bit of a rounding error there, but anyway, there it is, that's the theory. So we've got to show then that that is equivalent to 2.6 million suns. So what are we going to do? Well, we're going to need to take the mass of the black hole then and divide that by the mass of the sun, which we calculated earlier in question 2. So let's do that now. Well, in question 2, we got the mass of the sun to be 1.9 times 10 to the 30. We've just worked out the mass of the black hole. Let's work out that ratio then. Well, when I work it out, I get 3.7 times 10 to the 6. That's a rounding error, really. When you're using a number again, you ought to keep at least one more significant figure than you're going to round at the end. So by using both of these numbers to two significant figures, I've got a significant rounding error here in this one. Question said 2.6 million suns. I've got 3.7 times 10 to the 6, or 3.7 million. So I ought to have looked ahead and kept a record of the answer to more significant figures. But there we are. Anyway, the theory is correct. In fact, we've got a final part to the question. Apart from using equations that do not take into account relativity, state one reason why the two values do not completely agree. So I've got 3.7 million. They've suggested in their article 2.6 million. So even allowing for rounding error, we've got a difference there. What's that going to be due to? Well, the speed that we were given is only accurate to one significant figure. So they gave us the speed as 5,000 kilometers per second there in the article. That's only accurate to one, so trying to quote this to two significant figures, either 2.6 million or 3.7 million suns, is inherently inaccurate. The other thing is, of course, in using those equations of circular motion, we're assuming a perfectly circular orbit, and I would imagine this orbit is at least to some extent elliptical. It talks there about this year the star flirted precariously close to the black hole, coming within 17 light hours. So that suggests that at different times it's different distances away from the black hole, which would mean that its orbit was not completely spherical, or orbit not completely circular. So the fact that we've worked out basically here the centripetal acceleration in part 2 at the closest distance of approach, if it's coming closer at some times than others, it certainly won't be orbiting in a completely circular path. So our use of the circular motion equations is not completely valid, and that will account for some difference as well. Alright, 3b part 1. Write down the formula for the work done to remove an object of mass m to infinity if it is at a distance r from an object of mass big M. Well, we know gravitational potential at any distance around the object of mass big M will be given by v equals minus gm over r. So where r is the distance from the centre of this mass. So when we are a distance r from the centre of this mass m, the gravitational potential at that point will be given by minus gm over r. And don't forget, that's the work done moving a 1 kilogram mass from infinity to that point in the field. We know that when we're an infinite distance away from this object, then if r is in infinite distance, r is infinity, anything divided by infinity is 0, so v will equal 0. We know the work done on our object is simply m delta v, where lowercase m is the mass of the object that we're moving between these two gravitational potentials. So here we know the gravitational potential energy of a 1 kilogram mass at this point in the field. We know the gravitational potential energy of a 1 kilogram mass at this point in the field. To move it from a distance r away from the centre then to infinity, the work done will be the difference between these two values, which will be gm over r. That's the work done on a 1 kilogram mass. So to get the work done on a mass m, we just need to multiply the work done on a 1 kilogram mass by the mass that we're moving between these 2 points. And so what we will end up with, gm m over r. And there is our answer. Yeah. So here, this basically is the gravitational potential energy that a 1 kilogram mass has got, r, from the centre of mass big M. This is the energy that it's got when it's an infinite distance away, so the difference is the energy that it's gained, delta V. That's for a 1 kilogram mass. You just need to multiply that then by the mass that you're actually moving between these 2 points to find the energy gained by that mass. If the object of mass m, this is part 2 then, if the object of mass m has enough kinetic energy it can escape the black hole, estimate the escape velocity for an object 1 times 10 to the 10 meters away from the black hole at the centre of our galaxy. Use the mass of the black hole calculated in part 3. Right, okay, well, as you would expect, one part of a question is going to follow on from another. So here we've got the work done to move an object of mass m away from this object of mass big M from 1 point to infinity. We've got the same sort of question now here for the black hole. So we just got to work this formula out, basically. The work done, which will be the kinetic energy that it needs initially, is going to be 6.67 times 10 to the minus 11, big G, multiplied by, now the mass of the black hole we worked out earlier, and we got 7.1 times 10 to the 36 kilograms, whatever the mass of the black hole you calculated. And the distance from the centre of this black hole is 1 times 10 to the 10 meters. That's got to equal kinetic energy, so basically the work done to move it from a distance of 1 times 10 to the 10 meters from the black hole to infinity will be given by this value, and therefore that's going to have to come, that work done, that increase in gravitational potential energy of this mass m, is going to have to come from the kinetic energy that it had originally. M appears in both formulas, so we can cancel that out. And then if we multiply both sides by 2 and square root, we can work out V. So basically 6.67 times 10 to the minus 11 times 7.1 times 10 to the 6 divided by 1 times 10 to the 10. Find that, multiply it by 2, square root the answer, and what you will get is That's interesting. 3.1 times 10 to the 8 meters per second. Now, as soon as you calculate a value like that, alarm bells ought to ring. Have I got this right? This doesn't look right. Why doesn't it look right? Well, the speed of light is 3 times 10 to the 8 meters per second. So we've come up here with a speed that is greater than the speed of light. What does that mean? It says then part 3, comment on the value you have obtained. Well, clearly an object cannot have a speed of 3.1 times 10 to the 8 meters per second, and therefore it's not going to be able to escape from this black hole. In other words, basically if the escape velocity is greater than the speed of light, then not even light will be able to escape from this black hole. So there you are. Once something gets that close to the black hole, there is no hope of escape.